little more about statistics. So far, what we have talked about are population-based statistics. The summary statistics presentations and notes we've taken so far have been for analyzing every number in the population. And today we need to talk about inferential statistics. That's a little different. So I'm going to just show this slide here. So if we measure everything in the population, then that's awesome. But we can't always measure everything in a population, but we can still use statistics to estimate or forecast values which give us some very meaningful information. Let's say in class I use the example of what if I wanted to measure the width of everybody's nose. I could measure the width of everybody's nose in my class, and that would be pretty easy to do. Get the calipers out and then measure everyone's nose and write that down. And just, if I said the class is the population, I could use my summary statistics and that'd be just fine. But if I wanted to know the average size of a nose at Heritage High School, it would be inconvenient to try to measure everyone's nose. So what I could do is use my class as a sample of that data set and probably get a pretty good idea of how wide the average nose is at Heritage High School. So I would be estimating or forecasting the size of that nose based on statistics. The key idea on this slide is when you're talking about samples, you don't have a value for every member of the population. So we're using a smaller set of data than the population. Okay, this puts the two formulas side by side. You need to make sure that you get this formula noted in your notebook. And if you don't have this one, you should probably, if you don't have this one over here, population standard deviation, you need to write these down. So this might be a good place to pause the video, write these two formulas down, and then we'll talk about the differences. If we look at these two, you can see that they look really similar. The one on the left is for the population. The one on the right is for the sample standard deviation. And they look really similar except for there are two differences here. You can see that the bottom of this one is an uppercase N, which indicates the size of the population. That means every member is measured. And over here we have N-1, which is the accounting for the size of the sample of the population that you have measured. And the -1 gives us, it accounts for uncertainty. So if we don't measure everything in the population, we have to take away the 1 because there could be another value out there that's different. Is a way to think about it. So we do the number of samples that you have and subtract 1, and that makes it that accounts for that uncertainty. So usually when you do this, the population standard deviation will be a lower number because it's more certain than a sample standard deviation, which is going to usually be higher because of that uncertainty that we factor in. Okay, the process is the same for calculating standard deviation for a sample as it is for calculating the standard deviation of the population. You first calculate the mean. You subtract the mean from each individual data point. You square that number and then add up all of those numbers. Then you divide by the number of samples, -1, and then you take the square root of that result. And in class we went through an example of this, and we'll go through an example in this presentation in just a moment. But first we need to talk about this. Man, going too fast. Okay, this is how you calculate the sample mean. And if you look at this, it has different letters, but it's essentially the same as as calculating the mean for the population. Instead of the Greek letter mu, we're using X bar to mean sample mean. And we use summation, add up all the data points, and divide by the number in the sample. So it's add up the numbers, divide by the number you have, and you get the mean. This is a good formula to write down too. So let's take this set of data. We have 11 data points here, And so the first thing we would do if we were calculating the sample standard deviation, little s, we would go through and find the mean. So we add them all up and divide by the number there are, and we get a mean of 47.63 for this set of data. Now that we have that, we can take each individual measurement and subtract it from the mean and then square that value. So if we take 2 minus the mean, get that number, and square it, we get 2,082 and some change. And if we do that for all 11 data points, we get 11 numbers. And now we add all of these up and we get a sum. So if we add all of those up, we get 5,024. And then we take that number and divide by the number of samples minus 1, which is 11 minus 1 is 10. So we divide those two numbers. So we get 502.4545. And then we have to find the square root of this value because we've done this and this at this point. And when we do that, take a square root of that number, we get 22.4 as our standard deviation of this data set. And they have some notes about rounding in statistics. The sample standard deviation needs to be rounded further down the line. You need to have more decimal points than you do in your measurements or your mean. Okay, and that's what it says. Okay, we need to look at this important idea. We have two ways of looking at the measurements. For the population, we can have the mean, or we can have the population standard deviation. And over here, if we're talking about samples, we have the mean of our samples and the standard deviation of the sample. And let's read this as a sentence. As the number of samples gets closer to the number of members in the population, then our sample standard deviation is going to get closer to the standard deviation of the population. So what this is saying is the more measurements we take and get closer to the population, the more accurate our standard deviation is and the more accurate our mean is. So if you have 4,000 data points and you take a sample of 4, you will have an idea about what the mean is and an idea what the sample standard deviation is. But if you have 100 samples, you are getting numbers that are much more close to the actual mean and the actual standard deviation of the population. So the more samples you take, the better your results are going to be. And we're not going to do that. I want to go in and look at these probability distributions. So we've looked at these bell curves, and I'm just going to go straight to the pictures of the bell curves. So we've talked about a normal distribution, and if you do a dot plot and you can draw this kind of line that kind of outlines your data, you should see a bell-shaped curve, and the mean should be right in the middle. And another feature is it should be symmetric. So if you draw this line on the left side, you should be able to just flip it over, put it on the right side, and it's about the same shape and spread. So this would be a nice bell-shaped curve, normal distribution. Usually when this happens, your mean and your mode and your median are very, very close together. But something else that can happen is, okay, it's going through some more animation here. Something else that can happen is you might have something that looks like this, where your mean is kind of in this range here, but you have a lot of data that's over on the right side and not very much on the left. This is called a skew, or a skewness, or it's skewed. So this one is skewed to the right. If you put your mean right here, you can see the left side is not spread out as much as the right side. So the side that has the most spread is what we call it. So this would be a right skew. If you flip this around and the skew went the other direction, toward the left, and you had just a little bit, so if you took this image and flipped it over, then it would be called a left skew. So you find the mean, and wherever the mean is, the side that has the longer, more distribution, that's going to be what we call it. So this would be right skew. If you looked at the mean, the mode, and median they would be separated quite a bit. You would have very different numbers for those values because the median is going to be way different than your mean, and your mode is probably going to be way different than the mean. And I think that's all I have to say about that.